Okay, so today I want to talk about such thing as Fairfield realizations of different vertex algebras. So about this Fairfield realization in general, and also about what algebras can be obtained in such way. So, so far, we had one such example of realization of the Virasoro algebra in terms of some other algebra. Namely, we had free boson with the OPE of this form. Uh, and we could construct an energy momentum tensor in this form. So it's some normal ordering, but this normal ordering can be understood as usual bosonic normal ordering. No, equivalently, we can write that it is 1/2 G of Z G of Z. CFT normal product, it is the same. And if we write such representation, then this so we also have commutation relation which follows from this formula. Jm equals to n delta n plus m 0. And the relation that follows from this product is a relation in the Virasoro algebra. I won't write it here, but let me maybe remember how it looks like. We can remember it later when we try to check something. So it was one example. If you write it in terms of original field phi, the field which was in the action, we see that it corresponds to T of Z equals to minus 1/2 d phi squared. But there was also another example of classical theory. So it was kind of one example. Another example was classical Liouville theory, where we had something like dd bar sigma equals to mu e to the 2 sigma. And in this theory, we had energy momentum tensor, so some classical current, which looked like this. Maybe I can write down sign here. No, maybe it is just d to sigma. So let us check. So d bar t equals to minus d sigma mu e to the 2 sigma plus something like this. So probably there should be another factor 1/2 here. Probably yes. But it was a classical theory. But actually, I can guess that this classical theory comes as classical limit of some quantum theory of this Liouville theory, and we will study it later. But at the moment, we can notice that in principle there is some chance that there exists some more general formula for the energy momentum tensor in terms of this free field J. So, in a sense, we can try to construct this energy momentum tensor as 1/2 J of Z squared plus some constant times derivative of J of Z, like here. And we would like to check that so constructed field will have Virasoro OP. And so question is, what is this T of Z, T of W? So, and to compute it, I propose to use this operator state correspondence. Namely, I want to say that T of Z with T of W is sum over n. So original integer of T of Z, T of 0. Maybe so it will be something like this: n plus 2 ln vertex algebra f ln acting on L minus 2 on vacuum. And to compute this, we need to write some expressions from this lns in terms of generators of J. So we can write that ln equals to one half sum of m J n minus m normally ordered plus so DJ looks like sum of minus n plus 1 J n over Z to n plus 2. And this one equals to sum over of Ln over Z to n plus 2. So a contribution from this term is minus Q n plus 1 J n. So there is such a formula, and we can write first a few terms of. We can write first a few lns that follow from this formula. So where shall I write them? Maybe here and there. So L minus 2. For example, hmm? Yes, we are just checking if it is an geometric tensor of something or not, and then later we will understand that it is actually an geometric tensor of this quantum Liouville. Yes. Yes, so we just noted that there is some chance that a more general expression in terms of J will also be an energy momentum tensor of something, in the sense it will satisfy Virasoro algebra. Okay, L minus 2. So there is one term which contains J minus 1, J minus 1. It is for M equals to 1. So it is 1 half J minus 1 squared plus sum from n equals to 0 to infinity, and J n equals to 0 to infinity, J minus 2 minus m, J m. Because we will have pairs of such J's symmetric under m to n minus m. So then L minus 1, how to write this probably like this. L minus 1 is just sum from n equals to 0 to infinity J minus 1 minus m, J m. Oh, sorry, I forgot this last term here. So it is n minus 1, so it will be plus q j minus 2. Here we will not have this correction. So L0. Here again, I will have this term with 1 half. It will be 1 half J0 squared plus sum from n equals to 0 to infinity. It's and it's the only place where we really need this normal ordering. It will be J minus m, Jm. In this case, they don't commute, and there will be minus q and J0. Then L1, which is of this kind. So let me check if everything is included here. So probably it should be m from 1 to infinity, because otherwise we will include the term we will include the term j0, j1 twice. So, and if we take this, then there will be j0, j1, j minus 1, j2, and so on. This, so, and here, so is it fine here? So here we will have j minus, so there j minus 1 squared, then there will be j minus 2, j0, j minus 3, j1, no, maybe it's fine. So minus 2q and j1. There will be L2, which is here again we should take this middle term which appears with coefficient 1/2, j1 squared plus sum from 1, 0. Oh, sorry, here it is not from 0, it's from 1. And here it is probably from 2 to infinity. Something like this. Okay, so let us now use this to compute something. Yes, thank you. Yes, minus 3q j2, right? Thanks. So first, let us compute L minus 2 acting on 0. We take this term, and here this acts by 0 completely. So the terms act by 0. This one acts as written, j minus 1 squared plus q j minus 2 return vacuum. So there is this vector that corresponds to an energy momentum tensor. And now we want to act with all this else. Namely, we are interested in the singular part of this expansion. So n equals minus 2 is not interesting because it is regular. The first non-trivial case is n equals minus 1. So L minus 1 acting on L minus 2 turn 0 is so let us write this terms. It is j minus 1 j0 plus j minus 2 j1 And no, we should still write j minus 3 j2 probably. So and that's all. And the other terms act by 0. Right? So this acts on this. Now let us act with this term. Charges zeros, so it acts just by 0. There is also this term. It can act, so its action can be non-zero because this j1 does not commute with j minus 1, and it gives j minus 2, j minus 1, acting on a vacuum. And this last term also acts as non-zero. It will be q j minus 3. Acting on vacuum. Right? Yes. Thanks. And sign probably is correct. Yes, because they contain J3, J4, and so on that commute with everything like by 0. But let's now understand the meaning of this term. When we namely we had to compute this OP, we need to know to compute this OP, we need to compute this vector algebra, vector operator algebra map. So we want to compute y of this. Before that, let us look at our formulas. Maybe we need to write another formula here for L minus 3. And so let us write it. L minus 3 equals to sum from m equals to minus 1 to infinity j minus 3 minus m. Maybe it's better to shift it a little bit from 0 to infinity, minus 2 minus m, j minus 1 plus m. And plus plus 2q j minus 3, right? So we see here that this is the state we obtained is L minus 3 acting on vacuum. And now let us compute this matrix algebra map. Namely, let us try to look at the action of dt of z on a vacuum. So it is a sum of minus n plus 2 ln over z to n plus 3 external vacuum. So the term with L minus 2 vanishes because of this factor. And the first surviving term will be L minus 3. So L0, L1, L0, L minus 1 act by 0. So we will have L minus 3 with coefficient 1 plus sum from n equals to minus, so L equals to minus infinity to minus 4. Some corrections, and if now send z to 0, we see that dt of 0 acting on a vacuum equals to L minus 3 acting on a vacuum. So we can identify this state L minus 3 with operator dt. Y of 0 minus 3 on vacuum is dt of z. And so I told the last time that it is a general property. So because of such arguments, that if we have action of some different mode on a vacuum, it means the action of some derivative of a field. Because when we take derivative, we just shift indices in this expansion. So. In 0. Sorry. So is it fine? No, you can solve the computer at 0 because we placed operators inside in this point, but we can put here the arbitrary point. So it's kind of the main advantage of this operator state correspondence, and that Hilbert space of states in a theory lives at 0 or at infinity, and in general on some fixed radius surfaces that are chosen by when we choose how to quantize a theory, how to cut it into these slices. But at the same time, it is the same as space of operators. So if you work at 0 or at infinity, we work with this Hilbert space of states, and if you work at some arbitrary point, it's a space of operators. Okay, so we know this. We know that we know one term of this expansion. So so this is already computed. Now, so the beginning of this computation is here. Now another computation. Let us act with the next operator with L0. L0 is so it's 1/2 G0 squared plus J minus 1 J1 plus J minus 2 J2 and also minus Q J0. And this acts on again the state. So this acts by 0 because it commutes with everything. This one does not commute with the first term, and it gives J minus 1 squared. And this one does not commute with the second term. Plus 2 Q J minus 2 acting on 0. So it is 2 and L minus 2 acting on vacuum. So is it fine? So now the next question. What is L1 acting on the state? So we take this formula again. So it is J1 G0 J1 plus J minus 1 J2, and everything else acts by 0 because it already contains J3. And it acts on J 1/2 J minus 1 squared plus Q J minus 2 acting on vacuum. Hmm? Hmm? Where? Sorry, it's J minus 2. Yeah. And here I missed one term for L1 minus 2 Q J1. So it's in there. So is it fine? Okay, now so this term is by 0 because of J0. This I connect non-zero on the second term, and so it gives 2Q J minus 2 j minus 1, sorry. And this term does not commute on this one, so it gives plus minus 2q j minus 1 acting on vacuum. So it is 0, as it should be, right? Because the OP of Q of z does not contain term with z minus 3. So, and now the last term, which can be non-zero, because the other terms vanish because of because weight of this operator becomes greater than minus 2, and we should get some state of negative dimension, which are absent. Because everything is constructed just from this vacuum. So L2, L minus 2, return vacuum. So L2 is this one. So it is 1/2 J1 squared plus J 0 and J2 plus so by the way, at this moment we can notice that we have already one in a sense that we know that non-trivial part of the OP is correct. In a sense, we know that there is 2t of 0 and dt of 0 there. And now we only need to compute central charge of this algebra. So j0 2 minus 3 and j2 3q j2 So now again this term acts by 0. This term acts in some non-trivial way, namely it gives or 1/2 j1 j minus 1 from the first commutator, and then there is also this commutator, which is minus 6 q j. Yes, just minus 6 q. Yes. Minus 6 q squared. Acting on vacuum. So then we compute these two and get 1/2 minus 6 q squared. But we know that this should equal to C over 2 acting on vacuum. So if you now collect all this together, we see the following OP. So this is the most singular term. It is c over 2 over z fourth plus 2t of z over of 0 over z squared plus dt of 0 over z plus regular. And central charge equals to this one, but actually there is some parameterization that is better to do. Parameterization is the following. We denote this q equals to maybe, so I can miss this sign, but let us try something. I square root of 2 some big q. So in terms of this q, this central charge will equal to 1 plus 6 q squared. So, hmm? Yes, but commutation relation in the algebra is defined by a singular part. So in principle, if something goes wrong, we can get some new operators in this part, which means that algebra generated by something, by some generator, is not closed. We need to add more generators. But in this case, we were lucky, and this algebra turned out to be closed. But so there is another realization of this Virasoro algebra that has arbitrary central charge. And we can also see that this so where is this L0? So there is this formula for L0. So if we try to act with this L0 on some state which is eigenstate for J0 with some eigenvalue, but let us think what precise eigenvalue. So it is a little bit different parameterization from what we used before. Parameterization is the following, that eigenvalue of J0 actually on some state A is minus I square root of 2A. And there is such scaling. And let us compute the action of L0 on such state. So it is 1/2 of J0 squared plus minus I square root of 2 Q_J0 acting on A. So it is minus A squared plus probably I did something wrong. Here it should be not 1 square root of 2, but I over square root of 2. So that this becomes 1/2 minus 6 over 2. So yes, and this should be correct normalization. So it is I over square root of 2q, so it will be minus a squared plus a times q. So it is a times q minus a, acting on a. Hmm? We just take this Fock representation of Heisenberg. It simply does not have any other representation because it is some collection of oscillators. Uh, so Jn and J minus n act as Rosen-Lower operators for corresponding modes, and J0 commutes with everything. So its only option is to act by some number. Once we can diagonalize it. Hmm? What is different? In a sense, yes. Here we first studied the vacuum module to understand what kind of algebra we have. But then we can study different module of this algebra, namely this module that corresponds to arbitrary A. So it's at the end of the computation of this algebra relations, and now we go to this representation. So, no, it cannot be built without other operators because zero is defined by. So zero is a state that has a zero eigenvalue with respect to J0. And there is no operator that does not commute with J0. We need to add it manually to this algebra. In a sense, actually it exists in the full free-body theory. It is it is zero mod of phi. In a sense, J0 is momentum, and there is a coordinate operator in phi. Yes, because it's only a representation of Heisenberg. So J greater than 0. So now what else do I want to say? So I also wanted to say that originally we had this primary field J, but now it becomes non-primary. So we connect with L 0 and L minus 1 to see that they act by derivative and dimension, but let us act by by L1. L1 acting on J minus 1 equals to what? So this so where is L1? Mm, so it is here. So we need these two terms, G0 J1 minus 2 Q J1. So these two terms don't commute, and we get minus 2Q on vacuum, which means that Q of Z with J of Z with J of W equals to minus 2Q over Z minus W cubed plus J of W over Z minus W squared plus dj of W over Z minus W. So it is not primary. And it is actually easy to understand why it is non-primary, and because so we should ask why it's not primary. And also, if it is not primary, then it should be a descendant of something. And so the explanation is the following: we have L minus 1, which is written somewhere. It is written here. And no, wait, let me think. No, it's fine. So wait, what happens here? No, actually, I forgot. Probably there is no other explanation of this fact. Since you cannot write it as a descendant of anything. Yes, no, probably it's like this. So the only primary fields in this theory are now such states. Mm, and so what else can we say about this? Mm. Yes, it becomes non-conserved in a sense. If you look at the Liouville theory, then J is more or less d sigma, and when we do conformal transformations, we need to multiply this e to the 2 sigma by conformal factor, which means that sigma is shifted by logarithm of conformal transformation. So it is not it is not transforming a scalar, which and this is responsible for this term, and also for this classical part in the dimension of the exponential. So. Hmm? Yes, so this a term which is proportional to the to linear part of A appears because of the following. Then, if we consider e to the square root of 2a sigma and shift sigma by, so this is transformed as dw over dz over dw to power absolute value of it to power square root of 2 8, yeah, because e to the 2 sigma transforms as dz over dw to power 2. So we see that there is some that we have some dimension at the classical level, in a sense. Mm, Such exponential is multiplied by Jacobian of this transformation. So exponential with some other argument will be transformed in this way. So it is something. So it has a classical dimension, which is proportional to A, to linear part. And we see this term here, and this dimension consists of 2 parts. From this classical part and from quantum correction, which can be computed in the free theory. So it comes from normal ordering of the exponential, and this comes from this classical transformation law. Okay. Mm. Yes. So one comes from G0 squared, another comes from this. So, and they're here. Mm. Mm. No, a squared is a quantum because we obtained it just from normal ordering of the exponentials. So, of course, we obtained it in theory where this transformation was trivial at the classical level. This is quantum. Mm. No, by the way, there is also so there is this parameterization uh, dimensions, and there is also some nice parameterization of Q, namely. We have some field in this Liouville theory. So and this field should have a dimension 1, 1 because it is in the action. So this e to the to sigma should correspond to e to e to square root of 2 b phi in the quantum theory. So it is a field that should be written in the action. And so its dimension should be 1, 1. So that theory stays conformal. Out of this e to the square root of 2 d phi equals 1, 1. Since homomorphic and anti-homomorphic dimensions. And b is some parameter, and let us find the relation between this b and this q. So let us write in this equation that b times q minus b. So like this. So and this this should be understood as perturbation of Fourier theory with such exponential, and this mu should be dimensionless. Otherwise, it is non-conformal theory. So let us find the dimension of this. Let us find a relation between q and b. So we have some equation like b times q minus b equals to 1. to 1. Therefore, Q equals to B plus B inverse. And this is a very useful parameterization of everything. So in some sense, this parameterization linearizes a lot of formulas. So. And we also see some symmetry that there is some B to B inverse symmetry, which means that e to square root of 2 B inverse B inverse phi also has dimension 1. And the classical limit of all this is b going to 0. In this case, only one of these two b's survive. Hmm? Because when b goes to 0, yeah, we can rescale phi by b, and this becomes to go 1 over b squared d phi tilde d bar phi tilde plus mu e to the square root of 2 phi tilde. And actually there is another term here which I didn't write. There is a term with an interaction between phi and r. So this term will also become of this order, so it will be 1 over b. So it will become 1 over b squared phi tilde r. So all these terms, and mu can be rescaled in some way, because there is a freedom of shifting this phi by some number. So mu is not the actual parameter of the theory; it can be rescaled. So as a result, we see that the section is multiplied by 1 over b squared. So this one, this b or b squared plays a role of Planck constant. So we can write that this s equals to 1 over b squared s tilde of phi tilde. So when b goes to 0, this q goes to infinity, and we can neglect some of the terms. Basically, we can neglect we can neglect this quantum corrections. Okay, so well, the message is the following, that we can construct a generic representation of Virasoro algebra with generic central charge using just free boson. So sizes of the Varma modules are the same. So if central charge and this charge are generic, then they will be just isomorphic. In a sense, it will be a reducible Varma module, which is So as a vector space, it is the same in this Heisenberg module. Mm-hmm. Mm-hmm. Yes. Uh, the only problem is that in this way we can construct not the whole CFT, but some representation of this Virasoro algebra, because what we are missing is this collection of all possible vertex separators that can act between these Verma modules. Because we can construct something in terms of this free boson, but if we do so, we will have a charge conservation property. So the correlators will vanish in most of the cases. So it works only for representations. In some cases, we can use this operators with charges 1, 0, and 0, 1, instance homomorphic parts of this exponential, to do something with this charge conservation property. So they are called scaling operators, and they allow us to violate this charge conservation by some number of b's or b inverse. But it also gives us only some discrete set of vertex operators. So no, we can construct arbitrary module. We cannot construct vertex operators between these modules. So in principle, so we would like to have something like this: delta 0, delta 1, delta infinity, with arbitrary deltas. So let's write delta of a0, delta of a1, delta of a infinity. So, but the only option here is to say that that it is e to square root of 2 a1 5 1. But in this case, we will have a infinity equals to a 1 plus a0. So it means so it's the same as for the usual free boson. Such exponentials on the type such vertex spread on the type exponentials of phi give only vertex operators that act between these Raman modules with conserved charge. So it's not the full CFT; it's just a set of representations. So in a sense, so we can construct not this operator, but so we construct not such objects, but only a kind of set of all possible disks. We can realize any state in the Verma module in terms of free boson. So in some sense, it is a little bit better than just abstract Rama module because here we have some simple description of all these states. For example, we can describe them as polynomials of J inverse of J minus. So this Heisenberg of A is isomorphic to polynomials of j minus 1, j minus 2, and so on. And they are commutant polynomials. So Virasoro algebra acts on this on the space of usual polynomials of infinite number of variables by some differential operators. But if we instead try to take Verma module of the Virasoro generated by L minuses, they will be non-commutant polynomials. And it is not very nice. It is harder to work with. So, are there any questions about this? Okay, so let me type. Mm-hmm. Yes, yes, yes. There will, so later I will give some update about this because we can use this screening operators to violate charge conservation condition, but it will correspond to some integral representations of some simple correlators, and it will be just some discrete set. Okay, so this was a representation in terms of free bosons, but now let us talk about free fermions. Do you know all the story about Grassmann integrals and so on? The story about Grassmann integrals and so on. Hmm? Hmm? Ah, okay. So uh, then I'll just write some definition. So for fermions, for example, let us start from real free fermions. Is a theory with the action maybe so the factor in front of the action will definitely be wrong, and well, maybe with probability 1/2. But we can recover all these factors during the computation of the algebra relations. So it is this action psi d bar psi plus psi bar d psi bar d to z. This is conformally invariant if we say that square root of dz times psi is invariant. Because here we have psi psi and we have d bar, so d bar dz bar is invariant, and so psi psi times dz is also invariant. So because we have only psi and psi. In general, so if we consider complex fermions, um, also real means that they don't have charge. There is no U1 symmetry of the section. So what is called complex is this. So now maybe I can guarantee that one of these two signs is wrong, and they cannot be correct at the same time. So there is and they are complex because there is one symmetry that acts in the following way: psi star goes to psi star e to I alpha, psi goes to psi e to minus I alpha, and about this psi bars, don't remember precisely, but probably it should be the same. Bar star. Maybe it can be defined in different ways. I'm not sure. Hmm? Yes, yes, it is true, and so we will see that if we so there is a bosonization of this theory which passes from fermions to bosons, and one of the symmetries will correspond to a normal Yuan current, another one will correspond to topological current. But yeah, we can write this two holomorphic symmetries like this: psi bar e to minus I beta. So this is what means the word charged. And so there is also a natural generalization of this idea that we can write some vector-valued fermions, either complex or even real, and have some bigger symmetry group. And we're also considering this so non-abelian. So one option is to write psi I d bar psi I plus psi bar I d psi bar I d to z. Another option is to write by the way, what do you think? What are the symmetry groups of the sections? O. So could you say it again? O. Mm-hmm. In the sense that we have holomorphic and anti-holomorphic symmetry. Oh, in some sense, yes. And yes, here it is. Hmm? Yes. Thanks. Yes, one is holomorphic. Well, they are not scalars because they transform in this way. But, but it's a question how to define dependent or independent Grassmann scalars. So, in a sense, we can add some complex conjugation to the action, right, to make it real. And this complex conjugation should map psi to psi bar and vice versa. which means that so if the action is invariant under such a conjugation, then it means that if we apply this conjugation to correlators, they will also be invariant. So in a sense that if you conjugate psi and turn it to psi bar, in a sense all psis, then the correlators should be complex conjugated. And mm-hmm. Yes. So star is just about charge with respect to U1 symmetry, and bar is about being homomorphic or anti-homomorphic. They are unrelated. So, so in principle, it can be obtained from some two component spinor representation. But don't know if it is useful or not. Let's think. Uh, this one will be Majorana fermion. So if you want to make this theory massive, we can add only one term, which is psi bar, m psi bar. And this happens if we have psi equals to psi complex conjugate. And physically we know that Majorana fermions are fermions without charge. Right? So it is the most restricted case. And these are maybe yes, direct fermions because so we can see, for example, that in this case we can add different masses. We can add a Majorana-like mass, which is psi star psi bar. So in a sense, we can multiply them like this, or we can multiply them like this. One mass will have zero U1 charge. In the sense, it will preserve this charge. Another mass will have non-zero charge. So maybe so. And concerning the names, probably they should be called something like Majorana Veil fermions, but on this one, but I'm not sure. So if you want to write this, if you want to derive this action from, for example, there's a standard one with all these gamma matrices, it's doable, and we can try to do this maybe. But I'm not sure that it will work immediately. Maybe we need to fix something. To be honest, I don't want to do this because it is a two-dimensional case. We will need to find who is psi bar, how the Lorentz group acts on all this, who is complex conjugation. Maybe I would say that it is enough to to see that the section is actually Lorentz invariant because Lorentz group is embedded into this conformal transformations. So there are this boosts which no, so this is a Euclidean group. Euclidean version of it. So there are rotations that correspond to spin, and spin of this psi is 1/2. So, and the action is of the first order and derivatives. So it can definitely be written as some combination of Gamma matrices. But I don't want to do this. Okay, and now about. Sorry. Mm-hmm. Mm-hmm. So if you now compute the calculator of this size, it will be the green function of this Laplace operator. So some coefficient, no, not Laplace, but a d-bar operator. 2 pi 1 over d-bar. And so to compute it, we need to say that d-bar of 1 over z, so integral of d-bar of 1 over z, we should write this measure, which is dx dy. So it is integral d-bar 1 over z d z d z bar maybe times 2i, because it is x plus iy, x minus iy times I over 2. So this is with minus sign. Right, so it is minus I over 2, and now we can use a Stokes theorem. It is integral dz over z. So it is 2 pi I times this, which equals to pi. Okay, so probably the answer is that here it should be pi, and in the complex case, so here it should be 2 pi, and in the complex case it will be just pi. So and it is just factor of pi. So it tells us that so the bar acting on 1 over z is so in conclusion, the bar acting on 1 over z is pi times dot function. So 1 over the bar 1 over the bar of z w is 1 over pi 1 over z minus w. So it is 1 over z minus w. Okay. So in particular, we see that this fermions should really be Grassmann variables. If this function is so this function is is continuous. It just follows from this this Gaussian Grassmann integral. So we can check that psi of w, psi of z, so it's radially ordered, equals to 1 over w minus z. They change signs, and so we conclude that radial ordering of psi of w psi of z is psi of w psi of z when absolute value of w is greater than absolute value of z, and psi of minus psi of z psi of w when absolute value of w is less than absolute value of z. So in particular, it means that if we now use this OP to compute commutator between commutator of modes of this psi, it will be not a commutator but anti-commutator, because of this radial ordering exchanges them with a different sign. So, so if we now compute, so let's suppose that psi of z has some expansion. Also, this expansion is written as a sum over half integer modes, because our convention for all these expansions of CFT fields includes shift by dimension. P plus 1/2, so psi p over z, so p plus 1/2. So it's dimension, which is half integer. So we write this expansion, but to make this field single valued, we need to expand over half integer modes. So hmm? Because so our convention says that indices of mode expansion should be defined like this. a coefficient in front of 1 over z to n plus delta is has index n, but now we want this field be single valued around z equals 0. So psi of e to the 2 pi I z should equal to psi of z, because otherwise we will have some singularity at the origin. So this shift by delta can produce some square root, and this square root should be compensated by a half integer shift of indices.
So yet we could sum over q equal p plus 1 half, and then
But then we will have we will have z to q plus 1, right? And here we will have a p plus 1 half, right?
okay. But then we could rename. Okay, we could therefore p plus 1 half equal q.
Instance psi q.
And then we will get psi q minus 1 half, and then we could call it psi theta q.
Yes, the problem is that our convention is chosen in such a way that mode with number p shifts L0 by p. And in this case, so if you redefine q as p plus 1 half, you will evaluate this rule, and it is inconvenient. So of course people do like this, and it is actually super annoying, because also there is another thing that if p is half integer, we have positive modes. We have only positive modes and negative modes, and we don't have zero mode, which could have some eigenvalue. And if you shift p by 1 half, you will get some zero mode, which is actually a fake zero mode. It does not commute with some other operator.
I remember that there should be two choices, like the Ramon and then the Schwartz.
Yes, it is true, and this is an Schwartz. But if you go to the Ramon, so Ramon sector, such fermions will correspond to a non-trivial dimension at the origin. So the representation, so they will be non single valued around 0, which means that there is some field actually of dimension 1 over 16. So but it's different 1 over 16 than in bosonic theory. We will also study that case, but it will correspond to a different situation, because you see, if there is some special point, namely z equals to 0, and this psi has non-trivial monodromy around that point, it means that we lose translation symmetry, at least. Oh. So. Mm-hmm. Mm-hmm. Yes. So and in the Ramon case, so what changes in the Ramon case, we will sum over the integer p's, and in that case we will have zero modes of psi, which will act by 1 over square root of 2. So that square of psi is uh, uh, and commutator of psi with psi is 1. Yeah, but let us first study this case. So uh, mm, we can do it better. Maybe let us just imagine that we are computing this correlator by passing to uh, operator formalism. So, so we are computing this R psi of z, psi of w, for the case when absolute value of z is greater than absolute value of w. So this will be sum over p's that are greater than so over p's over q's psi p over z p plus 1/2 psi q over z to q plus 1/2. So, on one side. On the other side, it will be a sum of sum from n equals to 0 to infinity w to the n over z to the n plus 1. So, sorry, this is w to q plus 1/2. So, we conclude that so we just compare this two expansions and identify n plus 1/2 equals to n plus 1 equals q plus 1/2. So mean that q plus 1/2 should be strictly positive. Q plus 1/2 is strictly positive, and p plus no, it's not. No, it is for p plus 1/2, and q plus 1/2 equals to minus n. So minus n equals to q plus 1/2. And it is the only situation where this correlator, where this matrix element is non-zero. So if we sum these two, we see that p plus q should equal to 0. So So p plus 1/2 is strictly greater than 0, means that p is also greater than 0, because the other option would be minus 1/2 plus 1/2, which is 0. So p greater than 0, q equals to minus p. It is the only option when this matrix element is non-zero. So in this case, correlate of a matrix element of psi p psi q is 1. We know that since there will be is uh, scalar, in a sense it contains just one, it means that the anti-commutator of psi's are numeric. So looking at this, we can write that anti-commutator of psi p was psi q equals to delta p plus q, delta p plus q 0. Or in other words, anti-commutator of psi p psi minus p is equal to 1, and the anti-commutator of psi p psi minus q for q different from p. And if you change the index of psi by 1/2, this anti-commutation relation will have some strange form. It will be something like psi of p with psi of 1 minus p. So, or here we'll have psi p plus q, comma 1. And we will break this symmetry. Mm-hmm. Yes. Mm-hmm. So, in a sense, this is written a little bit inaccurate, uh, because uh, actually we should write that there is such expression, so we should have written it for some arbitrary states. There will be this state, there will be another, oh, maybe we can write it here, so there will be some matrix element between states A and B, and here it will be the same expression was permuted psi p and psi q, if you do everything accurately. But if you know that anti-commutator of psi's are some numbers, and that they are not zero only when p plus q equals to 0, it is sufficient just to compute the square root of 2 and find this anti-commutator. Hmm? Because OOP contains only numbers on the right hand side. So is it okay? Yes, yes. We cannot write anything else than this. So, so z psi w is 1 over z minus w plus a regular, and that's all. And also here we have just 1, because this is the first order call. We don't have any ends in it. Is such kind of computation fine, or is it better to do this computation with contours more carefully? Yeah. Mm-hmm. So it's basically the same computation as for the boson that had z minus w squared, but here we first change commutator with anti-commutator because they're fermions and this row should be changed. And second, we don't need to expand 1 over z minus w squared. It is just 1 over z minus w. So. Okay, so maybe that's all for today. The next time I'm going to construct an energy momentum tensor for this theory and compute its central charge. And then we will study this complex fermions and construct free boson from them, and also this non-abelian fermions to construct Cosmode algebras. Okay, so are there any questions?
Again, about this writing C as the sum of Cp over Cp plus 100.
Mm-hmm.
So in string theory, we define, first we talk about the, like on the plane, and then on, I think on the cylinder, and there was this 1/2 factor of difference.
Oh, it's different. These one halves are related, but in a sense, we also have NS and Ramon fermions on a cylinder. So if we go from plane to cylinder, we will need to take a square root of Jacobian of the transformation, which is a square root of the exponential. And let me write this. So on the plane we have psi of z times a square root of dz, which is sum of psi p over zp plus zp and square root of dz over square root of z. Then if I go to the plane, this z is e to w, right? Psi of so this form will equal to sum of psi p e to minus w times p times square root of dw. So this one becomes anti-periodic on a cylinder. Because so it's a kind of a general phenomenon then that when we go to cylinder, then this expansions in the exponentials does not have a shift by dimension, because this dz to power delta over z to power delta turns into just dw to power delta.
So I don't understand the argument of saying I have to pick this Daniel Schwartz because I don't want some branch cut.
Because we work on a sphere, and all points of the sphere are equivalent. Zero is not specified by anything. It is just a point where we decided to expand our field. We could take any other point.
So on the sphere I have just the shorts and I cannot have the Ramon one.
No, you can have, but having a Ramon field will mean that you insert Ising twist field at the origin. And I think they're also present in the string theory, and this twist fields. I don't remember precisely the construction, but they are definitely there. So. Hmm? Uh, Periodic in the sense that they're periodic when we go around the origin in one case, and in the other case we go around the cylinder. So those who were periodic on a cylinder become anti-periodic on a plane, and vice versa. Not on a cylinder, we don't have such arguments about single valuedness because 0 and infinity are already specified. So they inequivalent to the other points. And we'll also see the presence of this twist field from Virasoro representation, because this Virasoro representation that corresponds to NS will have 0 dimension, in the sense it will correspond to vacuum module. But if you take Ramon fermions, it will have dimension of 1/16, so it's not vacuum. And it will precisely, it will mean precisely the presence of twist field that changes a fermionic boundary condition. So, any other questions? Yes, thanks for your attention. See you next week.